my great pleasure to be able to introduce Alex Joseph and Yasmin Greenaway from Dermie.AI, who are fighting skin disease with AI. Alex is director of Elevate.AI and CTO of Dermie. He's an AI specialist, expertise in machine learning and trust and safety in those systems. And he pioneers AI solutions looking at large-scale societal challenges. Yasmin is founder and CEO of Dermie. They're looking at building computer vision modules to detect skin disease from imagery. They're being backed by Google, Hatch.vc, and Back.vc. Yasmin's a recognized speaker in the field, spoken at Oxford University, Health and Protect Insurance Summit, Warwick University Business School, and the Women of Silicon Roundabout. Prior to that, she was working in innovation at Barclays. So over to her.
Thank you so much for the introduction. So as mentioned, we are the founding team of Dermie.AI, and we build computer vision models for the early detection and management of dermatological disease. And so today we're going to be speaking about fighting skin disease with AI. And so as a quick introduction, as mentioned, this is Alex, this is myself. Really full circle moment actually to be here today speaking. So Alex and I met maybe 4 years ago, and we really bonded over attending the DSF festival. So it's a real honor to be here presenting to the community today. Prior to my time founding Dermie, I used to work in investment banking as a technical business analyst. And so what we used to do is something called entrepreneurship, where we take business challenges and innovate internally to create internal solutions. And so it was my job to kind of break the problem down into understandable components for our tech team, create solutions, and then roll them out internally to the business. And so just to give a quick overview of what we're going to discuss today, we'll speak about why health is such an exciting industry to be building in, kind of like the massive race from big tech companies to start innovating in AI. We'll quickly speak about the dermatology industry and how we're actually tackling solving the problem with AI. And so just to open, our mission at Dermie is to make the world healthier, and we're using skin and AI to do that. So one of arguably the best funds in the world, and probably one of the most famous, is Andreessen Horowitz, and they released an interesting quote. They said, "The most impactful companies are built at the frontier, and healthcare is the next frontier. It's time to put our tech skills to work. The mother of all markets is ripe for disruption." And that's a really interesting kind of like quote, because I guess we don't see the health industry as like frontier or particularly exciting. And what do we mean by frontier tech? So that means tech that's at the innovation edge, so cutting edge technologies that have the potential to disrupt an entire market. And that's where we're sitting at Dermie.AI. We're very much focused on tech for good because we believe in purpose-led innovation, and that's kind of what inspires Alex and myself to build. Deloitte has valued the health industry at 7.7 trillion. That's 1,000 billion. It's a massive industry, and there's a lot of opportunities for innovation and revenue generation. And I guess, as I mentioned, it's not really a traditionally sexy industry. It's very regulation heavy. But actually, there are so many barriers to disrupting that, in addition to like patient data, for example, not being very open, that it means that if you're successful in this space, you can really win. And if you look at some of the top 5 consumer-facing companies in the world, like Apple, Google, and Amazon, they're actually all racing to build in health, which is very interesting. And so you might be wearing a wearable, like myself, Apple Watch. Apple are behind the scenes using your biometric data and biomedical data to innovate health products. Google, it's very interesting. They're actually building a competitor to what we're doing called Dermassist. And Amazon are moving into health as well. So for example, Amazon Pharmacy, like allowing you to get prescriptions and having them delivered to your door. It's very interesting. And so it shows that startups in this space can have a really transformative effect on the healthcare industry. So I'll just play a quick video by former Google CEO Eric Schmidt, and he is kind of like outlining how we can use ML to find new ways to do things, and he gives a nod to why Derm is likely to become the next kind of like billion-dollar company. Let's see if the sound will work.
With whatever the dermatological problem is. Put that into my machine learning system, run it through the system, have it do a categorization, and then I'm going to go and sell the same service to dermatologists because my system will be more accurate than the individual dermatological diagnoses. So that model, which is you crowdsource information in, you learn it, and then you sell it, is in my view a highly likely candidate for the next $100 billion corporations. I'm not suggesting it would be Alphabet or Uber or Facebook, but if I were starting a company, I'd start with that premise today. How can I use this concept of scalability and get my users to teach me? Right? So if your users teach me and then I can sell to them or others a service which is better than their knowledge, it's a win for everybody.
I think what he said was so poignant because knowledge is not distributed evenly. Oh, they're speaking at the back. Knowledge is not distributed evenly. So how can we use tech to crowdsource knowledge and spread that around the world? Very interesting. So let's quickly look at some benefits of using AI in healthcare. Company you probably heard of DeepMind, right? So Google DeepMind have built a neural network model to highly accurately predict protein structures with their model called AlphaFold, and they trained it on 100,000 instances of protein images. And it's very exciting because what AlphaFold allows you to do is solve problems like antibiotic resistance, for example. So again, it's really interesting to see behind the scenes, most tech companies are actually focused on solving health problems. And so how can AI kind of like add benefit to the healthcare industry? We can help speed up diagnostic accuracy and diagnosis. As mentioned, sort of diagnostic accuracy is not equal. So your gender could determine how accurately you'll be diagnosed, your age, your race, for example. And AI are things that can all be helped, like solving these issues. So, of course, with all benefits, there are some risks and some very massive ethical considerations. I think one thing that I don't hear spoken about much is not just like the risks of the systems themselves, but it's the risk of human behavior in interacting with AI. And I'll give you an example. I saw a very positive paper detailing GPs using Google search, for example, and just armed with Google search, their diagnostic accuracy shot up. And that's a really good outcome. But for example, I read another paper where radiologists were measuring their performance of diagnostic accuracy against machine learning models. And actually, even when the ML models were wrong, the doctors deferred to the answer of the models. And that's really alarming because you need to start thinking about if a health professional is giving the right output, do they have kind of like the impetus or the confidence to override the output of AI? And those are the kind of like psychological impacts that we might have to think about when using AI tools as co-pilots, for example. Of course, there's a massive risk of unethical data use. Probably shouldn't mention this too widely, considering Google is one of our backers. But they were allegedly in the news for some potentially unethical data collection practices. And so even though the intention was there to create models that are trained on diverse and representative data sets, which is something that needs to happen, sometimes those methods of data capture can be quite unethical. So they were in the news for taking images of homeless people, for example, and allegedly swapping their personal data for AWS vouchers or something like that. But it just shows that there can be some practices in data collection and innovation that actually make people not trust. And so even though like now there's kind of like an open race where we can use people's data, in the future, if people start to revoke permission, what impact does that have on our ability to create innovation? And so why are we focused on derm? So derm is actually a massive, massive global problem. There are at least 2 billion sufferers worldwide. And when we mention derm, that covers things like skin cancer, psoriasis, acne, etc. Google, why they were building a competitor is because they see 10 billion derm-related searches every single year. So it's clearly an aggressive problem to solve, right? And this number is probably very understated because of differences in tracking and collection of health data globally. But even from the numbers that we can capture, it's costing a whopping $447 billion to our economy every year. And there's some exciting things happening in skin disease. So, for example, I think it was last month actually, a British man received the first personalized melanoma vaccine, and that's a skin cancer vaccine. And it was designed to help his immune system recognize cancer cells and start to fight them himself. Something that I really love about derm as well is that it's quite unknown, but there are strong correlations with comorbidities. So, for example, psoriasis, you may not know, it can be potentially an indicator of liver disease down the line. Acne, which seems like quite a tame disease, can potentially be an indicator of diabetes or cardiovascular disease later on down the line. So you can start to understand that actually by tracking skin disease, we can get better and better at early preventative care, because we can start to understand, okay, if someone has this disease day 1, what might they have in day 10? And those 9 days in between present a fantastic opportunity for early intervention. And so what's the specific problem we're solving here at Dermie? We are solving the problem of inaccurate, inefficient, and inaccessible diagnosis and treatment of skin disease. And so why are we kind of like doing this? Well, as you may or may not know, general practitioners, so GPs, are typically the gateway to care in the UK. But alarmingly, they're only doing 6 days of derm. And so that can sometimes result in the UK, and in the US the numbers are a bit higher, but I've read a few papers where GP diagnostic accuracy for skin disease is as low as 24% accuracy. And that is really alarming, because that means for every 4 people that go to see their GP, potentially only 1 is leaving with the right diagnosis for skin disease. And that's something that happened to me, right? I have a chronic skin disease, and it was misdiagnosed by my GP, and that kind of spurred me to start the company. And also the same happened with my aunt, whose skin cancer was misdiagnosed. It was actually raised in Parliament as well. There's only 1 derm to every 80,000 people in the UK, which is very scary considering skin cancer numbers are on the rise, and also numbers of dermatology consultants are actually lowering as well. So someone needs to be building a solution. And so what is our solution? To frame it in a very easy to digest way, Dermie.AI is a deep tech company building computer vision models for the early detection and management of dermatological disease. And so why have we chosen, and Alex will go into this a bit more later on in the presentation, but why have we chosen computer vision as a way to tackle this? Well, it's actually very compatible with derm for a few reasons. 1, because it's so visual and it can produce large amounts of data. And 2, because of the diagnostic practices typically don't require a biopsy, and that's great. Like, a lot of the diagnosis can just be visual, and so they marry really well together. And there are 3 SKUs which we can measure success of our models. 1, diagnostic accuracy. 2, efficiency. And 3, which is treatment accuracy and efficiency. And that's kind of like a combination of getting 1 and 2 right. So we won't go into it because we kind of have to keep this stuff still a bit secret, but this is just an overview of the way we are tackling the problem. I think one of the main differentiators between ourselves and competitors is that we have created a solution that allows people to capture longitudinal data. And if you're very interested in what we would do with that longitudinal data, feel free to speak to Alex and I at the end, because we're doing some really cool generative stuff. Another reason why this is the right time to be building is that there's an interesting convergence between hardware improvement and software acceleration. And those 2 factors have to be quite aligned to produce really good innovation. And I think it's like a point that's often missed, because if phone cameras hadn't been improved to the point where we could capture really good images, we probably wouldn't be able to release this kind of solution. And maybe 20 years ago, something like this wouldn't have been possible. But the convergence of hardware improvements and software improvements creates an exciting environment where a solution like this can potentially work. And it facilitates the capture of images for skin disease diagnosis remotely. And now, just to speak about some of the different ways some of our competitors are approaching this, so for example, skin analytics, they're very much hardware focused. And so typically a derm would use an attachment called a dermoscope to actually really see what's going on in the skin very specifically. But what that does is that it actually kind of chains your models to uses in a very specific setting. So if the doctor is not kind of like the one uploading the images with their dermoscope, it's very difficult to transform those models into other environments. And this is why we chose to use clinical style images rather than medical style images, because clinical images can be recreated in your home. And so this is just an example of what the difference between clinical images and medical dermoscopic images look like. And so you can see in the first image with the dermoscope, there's like this interesting kind of like black circle. And those kind of like image interferences can create challenges when creating models. Oh, now I'll hand over to Alex, get into the meaty technical stuff. All right,
Thanks,
thank you so much.
Okay, so thank you, Yasmin, for a great introduction to what we're trying to build at Dermie. Now, as you can imagine, a large part of what we're trying to build is, of course, AI. And in this section, we're going to dive deep into just how we've built our AI pipeline. Now, we're going to do this in 4 sections. First, we're going to tackle a problem definition, really get concrete into what we're trying to build here and what success looks like. Then we're going to cover some of the challenges that we faced and that anyone will face in building an AI pipeline like this one. And then we're going to get into the data collection. What sort of data sources are there and what other data sources we've used. And finally, we're going to finish up with model architecture, my favorite part. And any data scientist in the room is probably going to appreciate this part. We're going to dive deep into the model architecture and discuss some of the benefits and drawbacks of the different approaches. So first, a problem definition. Now, what we're trying to do here is automated skin disease detection. We're trying to detect skin diseases in clinical images. Like Yas mentioned, a dermatologist is typically going to see 2 types of images, clinical and dermoscopic. Dermoscopic images are taken with specialist hardware and are often sort of more zoomed in to the skin lesion itself, whereas clinical images are often more zoomed out. You can often make out the body part that the skin lesion is present on, for example. So we're focused mainly on clinical images because we're asking our users to take pictures on their smartphones of their skin lesions. Now, just to add a bit more context, so this is an object detection problem. We're not just interested in classifying whether an image contains a particular skin lesion or not. We also want to locate the particular location of the skin lesion, as shown in the bottom left image here. So yeah, this is an object detection problem. So we're clear on what we're trying to do here, but what does success look like? Now, Yas mentioned that GPs typically have a 24% success rate. In this particular paper, so I took this table from a literature review, they reported that GPs have a 50% success rate. Now, that quickly improves when you compare that to expert dermatologists that typically have a roughly 80% success rate. Now, at Dermie, we've set ourselves the task of matching the experts in this field. We're trying to reduce the workload of these dermatologists. As Yas mentioned, there's 1 dermatologist for every 80,000 people. So we really need to match that accuracy. Now, although this table mentions accuracy and uses accuracy to compare different medical practitioners, in actuality, the data scientists in the world, who's a data scientist in the audience? Raise your hand. Okay, cool. Yeah, so you guys will know the F1 score is usually a better measure of model performance, and especially in this case where we're facing an imbalance problem, most images we see will not contain a malignant skin lesion. So F1 is a good measure of model performance when you're facing some imbalance issues like this. So in building this pipeline, of course, we face a couple of challenges. Now, these are a couple of images, well, 3 images from our data set. One of the biggest problems we're facing is variation in images. Now, our users will take pictures of their various skin lesions from different sort of distances from the skin lesion itself, which introduces a lot of variation to the images. Also, they'll take pictures in different lighting environments, different environments. All this makes the problem more difficult for us and for our models. The other issue is a lack of data. There's a severe lack of dermatological data, and also there's a big problem with representation in these data sets. Now, most of these data sets don't report their race and skin tone distribution. We found just 17% of data sets do. And that is a massive problem. Now, most of these data sets don't contain much representation of darker skin tones. And what that eventually means downstream is that a model, and the data scientists in the room will know, a model trained on these data sets will underperform on darker skin tones. Now, there's a few reasons for this. One of the reasons is that certain skin diseases are less likely to be represented on darker skin tones, for example, skin cancer. But it's definitely something that needs to be tackled, and you usually need a large, diverse data set to build an effective model here. That being said, we have identified a few data sets. Now, in the dermatological literature and the open source data sets available, most of these data sets won't be available for commercial use, so they're research only. We have identified a few that are. One thing that you will know is most of the data sets have very few samples. So that is also a sort of issue that needs to be addressed in this domain. That being said, the Google Skin dataset, which is brand spanking new, so this dataset was actually released in March of this year. What makes this dataset interesting is Google collated this data in an interesting way. So being Google, they have access to Google search data, right? So what they did is they targeted people that were searching for solutions to their skin diseases, and then they essentially asked them to upload images voluntarily of these skin diseases. And they managed to get 5,000 people to upload images with, they were able to create a data set of 10K images in total. Now, what makes this data set particularly interesting is the different sort of skin lesions that are represented and the variation in the images themselves. So I've included 3 examples here. So we've got herpes, we've got a skin burn, psoriasis, a large variation of different skin lesions, and of course you can see the variation in the images. Now, if you can conquer this data set, you can do anything in the dermatological field, but I wanted to highlight this as a very useful source of data, especially given the fact that in dermatology, the lack of data is a really big issue. Now, at Dermie, we're lucky enough to have an extremely large data set. So through our skin tracking app, we managed to get over 100,000 downloads with 40K people uploading images of their skin. And what that led to is essentially over 1 million images of skin and skin disease. So we've essentially got one of the largest, most diverse skin data sets in the world, which is something we're really proud of. So data isn't an issue for us. That being said, we did need to add some essential metadata to it. So a dermatologist in the real world is going to take into account a patient's skin history, age, and also the particular area on the body that the skin lesion is presenting before making a diagnosis. Now, many of our images lack this crucial metadata, so we turn to open source models to help us and assist us with this. So we did this in a couple of ways, 2 of which are shown here. Now, first of all, we use a vision transformer, which is an open source computer vision model. We use that to detect the ages being represented in our dataset. And then we also use Clip. Was anyone in the video talk just previously? Show of hands. So they mentioned Clip as a very useful model. Now, what's useful about Clip is you can use it in a way that is called zero shot. Basically, you can tell it to identify specific things in an image, and it will work out of the box. And the way we're using it is to identify specific body parts in our data set, basically. And this has worked really well. For example, we were able to unearth that 40% of our users that uploaded images were in the age range 20 to 29. This makes sense, right? We can expect younger people to usually use apps, especially a skin tracking app. So we've got our data set. We've been able to retrospectively add in metadata. Now, the next step, of course, is data labeling. We need to prepare our data set for an AI model to learn how to detect skin lesions in it. Now, being that we're trying to create a model in the medical domain, we need to take extreme care in how we create our data set. So each of the images in our data set are labeled by a minimum of 3 dermatologists, they're experts in the field. And remember, this is an object detection problem. So they're identifying skin lesions, shown in the boxes here, and they have to draw a bounding box to identify its exact location. And then we can use this data to train an effective model. So once we've got our data set and we've labeled it, we've sort of prepared it for a machine learning model to learn from, the next step is training. And now, the first step in that is, of course, pre-processing. The data scientists and machine learning engineers in the audience will know. Now, being a computer vision problem, there are some standard ways you want to process your data before training. Now, you want to make sure that all your images are the same size, for example, but you also want to add some data augmentations. Now, augmentations essentially have the effect of making your data set more diverse and allow you to create a more robust model that is more likely to perform well in production and for like real users in the real world, essentially. Now, in the computer vision world, there are a few standard things you want to do, some of which are shown here. So you want to take an original image, you want to do things like shearing, reflections, rotations, to create new data that is slightly edited and basically allows your model to learn that you want to detect a skin lesion at different angles, different levels of zoom, that sort of thing. Essentially, you want it to make it more robust. Now, these sort of data augmentation processes are quite simple, but people have also explored generative AI and used it to augment data. Now, generative AI models are things like OpenAI, DALL-E. They're capable of creating new images from an input image. And I wanted to show you some of the potential pitfalls of using such data augmentation processes in this presentation today. So what you see here is an image of someone's knee with a skin lesion. You can see the reddish bump highlighted here. Now, I put this image through a closed source. So this is a closed source company. They offered a data augmentation service using generative AI. And I wanted to see what happens when you run this image through it. Now, what you can see is in the first image, the knee is still there, but unfortunately, the skin lesion has been removed, which is, of course, catastrophic for our use case. But things get progressively worse. In the next image, what you'll see is what was once a knee has become some sort of furry orange animal. Again, the skin lesion isn't recommended, but again, things got worse from here. In the final image, what was once a knee has become some sort of monster. And I mean, it looks like the skin lesion has become an eye of some sort. Now, of course, you don't want to put this into your data set. This is going to confuse your model. But it just goes to highlight some of the problems we see using generative AI data augmentation. Now, that being said, I am being quite harsh on generative AI. You do need to tailor-make your generative AI augmentations to your specific use case. And this is an example of someone that has done this. Now, I've taken this image from a paper in the literature. And what they've essentially done is show the original image on the left, and then different augmentations and sort of edits going throughout each row. If you think back to one of the first slides that I presented, the differences in lighting is a real issue for us. And in this paper, they were able to show that a generative AI model can create different images with different levels of lighting and with lighting at different angles. But what was super interesting about this paper is the disease impacting. So essentially, what they were able to do is take a skin lesion from one image and then paint it onto someone else's body in another image. And what this has the effect of doing is essentially creating new data, which again, the more data the merrier in machine learning, is something that's really useful. So generative AI is something you do want to use. We're not actually using this in production. It's quite an involved process to create this disease impacting, etc. But I thought it was worth including. Okay, so we've covered our data source, we've covered pre-processing. The next step is choosing your model architecture and, of course, training. Now, is there anyone that has worked in the computer vision world for at least 10 years? Quick show of hands. Okay, no one. So before deep learning, handcrafted features reigned supreme in computer vision. Now, a couple of them are shown here. Handcrafted features are essentially algorithms that have been created by humans to mimic certain heuristics. So, for example, the SIFT algorithm was created to highlight distinctive features in an image that are robust to transformation. So, what remains true about an image no matter how you rotate it or reflect it? Then we have ABCD features. Now, in the real world, dermatologists use something called the asymmetry, border, color, and diameter metric to determine whether a skin lesion is malignant or benign. And people have tried to replicate this process in computer algorithms, which, of course, as you can imagine, can be extremely useful. Now, whilst these handcrafted features are quite old school, they're more traditional algorithms, they have been shown to outperform deep learning methodologies. So in one paper, handcrafted features combined with a traditional machine learning model, an MLP or decision tree, outperformed a VGG, which is an example of a deep learning model. That brings us nicely onto deep learning. Now, deep learning models revolutionized the computer vision field, going back to the 2010s. And in the early days, CNN's role reigned supreme. Now, these models are often trained on datasets like ImageNet. ImageNet is basically a large dataset showing different types of images, and it allows your model to sort of learn different types of object representations and get a real feel for image classification and object detection. Now, CNN's rule supreme and are still effective, but then in recent years, the transformer architecture that was made popular in the NLP domain, for example, ChatGPT makes use of the transformer architecture. This transformer architecture was taken from the NLP or text domain and then applied to computer vision with great success. And the vision transformer became state-of-the-art in a number of computer vision problems. So you want to consider both of these models. Now, the vision transformer model is often more computationally expensive to train because of that transformer architecture that learns to pay attention to specific parts of an image. And also, these models tend to need a lot more training samples compared to a CNN. And just to highlight the effectiveness of CNN, so what you can see is on the bottom left-hand side here, the VGG and the ResNet CNNs were able to match that 80% accuracy that we're looking for on a dermatological dataset. Now, the final model architecture that I want to highlight is the multimodal architecture. Now, in the video talk previously, they highlighted some of this. What a multimodal model is essentially is a model that's been trained on various different sort of data types, usually text and images. Now, because these models are massive, they've been trained on massive amounts of data, it makes them very data efficient at learning new things. And it's been shown that if you train these models on a data set, okay, let's say we've got a data set of 30K images. If you take just 10% of those images, 3K, and train a model on them, you will get 90% of the performance as if you trained it on the full data set. So they're incredibly data efficient. And also, many of them are instruction tuned, which means you can essentially talk to them like I've shown in this image here. Now, this is an open source model called Lava. It's open source for everyone to use. Now, we have explored using closed source models like GPT-4, for example. The problem is they have very restrictive licenses, and they don't actually want people performing medical diagnosis using them, and you actually get banned, basically, if you don't have like a prior agreement with them. So yeah, you probably want to use open source models. Now, because these models are so large, you probably need to use techniques like low-rank adaptation or quantization to speed up the training process and make these models smaller, basically, so you can train them on consumer hardware. So that being said, at Dermie, we've gone for a hybrid architecture. We're combining the traditional handcrafted features with a CNN of our own creation, and we're putting that into an ensemble, which basically means we're combining these two approaches together. And we've managed to create something that's really impactful in production. We've managed to match that 80% accuracy that we see in dermatologists in acne, eczema, and skin cancer detection. And also, our in-house dermatologists have been able to rapidly speed up their diagnostic rate by 60% in using our models in diagnosis, which is amazing. They can see, it essentially means they can see more patients per day. And then finally, we're ramping up our models to be able to detect 1 million images a day. Now, when you compare that to a single dermatologist that might see maybe 30 patients a day, we can really make an impact here, especially when you consider the fact that most people in the world are extremely far from a dermatologist. So it's something we're really proud of.
Good timing.
Yeah.
So with that, thanks, guys. So this was a very short segment, and so there's so much more we're doing in terms of like other Gen AI techniques. There's a lot of things we're really excited about. We know that we have some of the smartest minds in the room, so we'd love if you were to reach out to us and ask us any in-depth questions or understand a bit more of the exciting things we're doing behind the scenes. I think it's such a new and unfolding field that there's a great opportunity to put out literature. And so these are kind of the things we're working on as a company as well, like putting out some pioneering papers. I see Sarah nodding. She's very pro-literature. So feel free to reach out to Alex or myself, if you want to chat more.
Great.
Thank you, guys.
Thanks very much for that really interesting talk. I'm sure there are a few questions in the room.
Thank you so much. It's really interesting use case with computer vision model. The vision model is actually really great performance for especially the visual side. And also dermatology is pretty good field to use this technology for sure. But I think that could be a bit not enough, let's say, because there are some symptoms that cannot be captured with the visuals, for example, heating or like itchiness and this kind of thing.
Yeah.
And earlier, some of the slides shows you use the age classification or body body detection, which body part it is, and I guess that is also used deep learning models to do that process as well. And I think like why did you have you thought about like having users to give you this input as a which body part or like this kind of symptoms and use those data as a hybrid model together with the computer vision, or what? Or did you just go directly to like fully computer vision model to be implemented? So I just wanted to hear the opinions about that.
Fantastic question, great question. So I'll take the first half and then Alex can take the second half. So exactly, and so we didn't really go deep into our solution because we're quite stealthy about it. But we are creating mechanisms where users can capture signs and symptoms. And so, for example, let's take like skin cancer. You should actually be looking at suspicious lesions at least every 3 months, recommended every month, and that's per NHS guidance. And so at each month or 3-month checkpoint, you should actually be looking at if there are any changes in signs and symptoms. And those are the things that will capture what you're speaking about, like itchiness, et cetera, et cetera. So we are building that kind of like data capture. As mentioned, we are a longitudinal solution, whereas typically we're seeing our competitors in the space just like kind of like one-off use solutions. But to your point, dermatologists, the reason why I like dermatologists and doctors in general is because they're actually like human like decision trees. Like they follow a decision tree and validate or invalidate their assumptions and hypotheses with each question. So if you go to your doctor, they're probably asking you loads of questions. You know, did you travel outside of the country? Have you changed your like washing conditioner, for example? And they're doing a decision tree in their mind. And those are the kind of like instances where you can capture those signs, symptoms, or like other contributing factor changes. And that's what makes them really cool to replicate using tech, for example. Not that we're trying to replace doctors in any way.
Yeah.
And Alex can take the second part about like body capture and stuff.
Yeah, so I think you're basically saying there are many features that need to be taken into account when you're doing skin disease diagnosis, basically, and that's completely true. So whilst I highlighted two in the presentation, we are capturing more. And like Yas says, in the app, our users are telling us what body part the skin lesion is located on. And they're also doing things like, we're also enforcing things like improving the quality of the pictures that our users take, for example. Yeah. But that wasn't the case early on in the app's history.
The first iteration, yeah. You're welcome. Very strong shooting.
Thank you for the very interesting talk. I don't do image processing, but I was wondering, now phones add AI-generated texture to images to improve sharpness. How do you deal with that? Because that can change indeed, you know, the mole shape, etc., etc.
Yeah. So this is something that we're just beginning to think about now. Where AI sort of edits the user image, that can have a negative effect on our models. So where possible, we want to take the original images that hasn't been edited by AI and sort of push that through our AI pipeline. However, certain things like resolution can also can be okay. A super resolution, that is, again, covered in the NVIDIA talk. But it's really a case-by-case basis. And the main way we want to address this is by enforcing sort of requirements on the user side in terms of what images they can take through our app, if that makes sense.
And also just to tack on to Alex's point there, having over 1 million images now with downloads from around the world, right? We have a very large distribution of different types of devices when they were released, like camera resolution, etc. And our data was like sourced from around the world. So for example, I think if I remember off the top of my head, 25% was from North America, about 19% from South America, about 14% from different parts of Asia, etc. So we're like a 60-40% iOS and Android split. So we get a lot of variation of like types of images. So it's really useful to see like different like kind of like use cases and stuff. Yeah.
We have another question here.
No.
Yeah, thanks. So I'm from New Zealand, a certain age, and so we're really at high risk. And so ever since I've been in the UK, I've had a check. It started off as a check every 6 months with a registrar, a proper dermatologist at St John's. And now, as time goes by, this is to going the idea of the challenge to the NHS for trying to manage these conditions at scale.
Yeah.
And now it goes down to an annual thing where they do comparison with medical photography.
Yeah.
And it's done by a junior person and often not even a doctor.
Yeah.
So having access to medical photography, would that be a good thing for you? The problem being that you then have to deal with a lot of lesions on a large photograph. Can you do that? Can you scrape down a larger image to look at individual lesions?
Sorry, what is it you're asking? Sorry, rephrase the question a little bit. So are you saying like images taken in a medical kind of environment, are we able to use those? Is that what you...
Yeah, so they're taken in a medical environment, taken with, in a controlled environment with proper gear for doing diagnostics.
Yeah.
But they're taken of large areas of skin from distance.
Yeah.
And they're used to do that comparative piece. So it seems to be a problem that's been crying out for the solution. And I have this conversation with dermatologists for decades. So are you able to then take a large image and then screen that? That's the question.
So we haven't kind of like looked into that for now. It's interesting because the space is... There are a few players moving into the space, right? People were actually really grateful for their work as well, because when loads of people are starting to build, it progresses the field. So to name like a few of our like co-workers, I wouldn't even call them competitors, right? Skin Analytics, Skin Vision, Legit Health in Europe, Visual DX in the States. Like a lot of them are actually focused on medical style images. And one thing, it's so interesting, like we need to make these decisions really early because the types of data we collect has impact on where those models can be used. And where we saw kind of like our competitors really focused on images taken in specific environments, we actually went the other way and focused on kind of like user captured data. And the reason we made that strategic decision very early is because we didn't want to tie the models to uses in a very specific setting. When we're thinking about health equity as a measure of success for us, it's making sure that those models are usable around the world with people perhaps in underprivileged countries, for example, or who can't access a doctor, or maybe if you're extremely privileged but the wait list is a year, for example. If your models are kind of like only used in a medical setting, it kind of like chains the performance to those specific types of images. But to your point, it's something that we wouldn't rule out in the future, and I think it's definitely smart. It's interesting, like our chief medical officer, not our chief medical officer actually did contribute maybe 50,000 proprietary images throughout the time in her medical career as well that were already labeled, and they were more standardized. So it's still very useful, and they happen to have been captured in India, which again is a massive success for us because we typically wouldn't see that large amount of data on the Indian population here already labeled, ready to go. But I say all that to say in the future we would definitely do that. But I think because we saw most of the industry rushing to solve it that way, we kind of wanted to solve like the health equity problem. Yeah, that's a very long answer, but...
Right. I think I need to let you get to coffee, but I'm sure Alex and Yasmin would be happy to take questions if you come and catch them outside.
And we'd love you guys to email us as well. Yeah.
Let's thank them again.
Thank you. Thank you, everyone.